Morning, everyone. Today I'm gonna talk about new chapters about circular motion, but you will see this is nothing but the Newton's second law again. Okay, so first we're gonna talk about uniform circular motion, which means the speed of an object moving along the circumference are constant. So, for example, here we have an object. For example, here whose speed is 10 meter per second. And then the speed of a object here is also 10 meter per second, and same here, 10 meter per second. But now think about the definition of the acceleration. Definition of acceleration is the delta v over delta t. So that means velocity changes will cause acceleration, right? But it seems like there's no changes in velocity. But now make sure velocity consists of two parts because this is a vector, right? So velocity consists of a magnitude and it's a direction. So the magnitude part of a velocity is a constant for this example for uniform circular motion. However, direction of the velocity here is northeast, here west, here southeast. Do you see the direction is changing? So because of this direction changes, acceleration will be caused. And we call it centripetal acceleration, whose magnitude is a v square over r. And then the direction of this centripetal acceleration is always toward the center of the circle. So the ball at the end of a string is being swung on a horizontal circle. So basically, let's assume you have a table here, and then you have a pivot point here, and then you have a string, and then this is pivot, and then you have a ball, and then this ball might have a circular motion on this plane. And then the ball is of course accelerating with the centripetal acceleration, whose direction is to the center of the circle. And then we have again this acceleration because the velocity changes. Again, velocity changes, so you have two things, right? You can either change the speed of it or direction. So the answer here is velocity is a direction, velocity vector's direction is a changing. And the same, read the same question. The car is turning on a tight corner at a constant speed. So constant speed meaning that your speed, in other words, magnitude of the velocity is constant. And the top view of motion is shown here. And then the velocity vector for the car points the east at the instant shown. What is the direction of the acceleration? Direction of the acceleration is always again to the center of the circle. So the direction of the acceleration is down. And then similar question, a ball, same situation, ball on the table, swinging. What is the direction of the acceleration of the ball? Again, toward the center of the circle. So the answer is B. And now I'm gonna introduce new concept, two new concept, frequency and the period. So I can start with the period t. So period t is how long will it take to complete one cycle of the motion. In other words, how long will it take to complete one revolution of the circular motion. So that is called period. And then also we have a frequency whose concept is what? How many cycles you can complete in 1 second. In other words, the number of revolutions are per second. So for example, let's say t is zero point 0.5 second. That means if you assume you start the ball, start moving from here and then come back here, and then it will take a zero point 0.5 second, right? So then your question is, what is your frequency? In other words, if you can complete one revolution in 0.5 seconds, how many cycles can you complete in 1 second? So your answer is a 2. So frequency has a unit hertz. So then now from this relationship, you can guess frequency is a 1 over f. So in other words, for this case, our frequency is 1 over 0.5. So you have a 2 hertz. Or t is a 1 over f. So again, frequency and the period, they have a different physical meaning. Again, period, how long will it take to complete one revolution? Frequency, how long will it take, how many cycles how many revolution you complete in 1 second. So basically they have two different, their own physical meaning. But mathematically, as you see here, if you see one of them, you see the other one. You can find the other one immediately, right? So mathematically, they are equivalent. And then another concept here is the velocity. So the velocity, for the circular motion, assuming again you start from here and then come back here. And your velocity is the distance you travel, which is 2 pi r, assuming the radius is r, and then divided by t. That's what the physical meaning of the t, right? How long will it take to complete one revolution? So your velocity is also 2 pi r over t. So assuming r is a constant, so then now if you know v, you can find the t and you can find the frequency. So even though these three has a different physical meaning, they are equivalent. So I'll call them it's just a family members. So if you, in other words, again, if you know one of them, you can find the other two immediately. And as we defined, acceleration of the center of feather motion is a v squared over r. But sometimes v is directly given to find your acceleration, but sometimes the frequency is given, but you can still find the v, right? Why? V is a 2 pi r over t, but 1 over t is a frequency, so your velocity is a 2 pi r, 2 pi fr. Or you can also express your v in terms of a t as well. Again, the thing is v, t, frequency, they are the same family. If you know one of them, you can immediately find the other two. So for example, another family member is a RPM. So for example, here you see the first sentence, a circular blade of a table saw is a 25 centimeter in diameter and spins at 3,600 RPM. So maybe most of you know what is RPM. What is RPM? 306,000 RPM. So that is a revolution per minute. So this RPM concept is, you see, it's almost the same as a frequency. The only difference is here is RPM is a revolution per minute, which means revolution per 60 seconds. But frequency is what? Revolution per second. So this is nothing but if you convert RPM per 60 seconds, right, instead of a minute, then now you see this is gonna be 60 hertz. Right? So you can immediately convert RPM to hertz. Why? Because forget about the formula, but now you just think about, okay, I have a 3,600 revolution per minute. So that means in 1 second you have a 60 revolution. That means your frequency is 60 hertz. So then we have a one more family member. So frequency, if you know frequency, you can find the t, you can find velocity, you can find the RPM. In other words, if you are given one of these four, you can find the other three, immediately. Okay. So for example, let's say your RPM is given, but now you can find what is a hertz. And then how much time is required for one revolution. Because now you find the frequency, your period t is simply 1 over 60. This is your period t. And then how fast is one of the t's at the edge of the blade moving? So that means you're looking for the velocity, right? And your velocity is what? Your velocity is a circumference, which is a 2 pi r divided by time. How long will it take? Period t, 1 over 60. That's it. Where your r is a 25 centimeter, diameter is a 25 centimeter, so your r is the 12.5 centimeters, so that's gonna be 0.125. So If you insert r 0.125, you can find the velocity. And then what is the t? Is acceleration, for the circular motion, center feather acceleration is a v squared over r, right? So now we know what v is, we know r, so you can find the answer, right? So your frequency, again, is a 60 hertz. So you can find your t is 1 over frequency, is a 0.017. And then now you can find your velocity, which is a 2 pi r over t, right? So 2 pi r over t, or frequency, right? So you have a velocity here. And you can find your acceleration. Of course, you can use a frequency, but you can basically use a 1 over v squared over r as well. And then you can double check, you will have the same number here. So the dynamics of a uniform circular motion is exactly same as what you did for chapter 5. Chapter 5, main idea of chapter 5 is what? Once you choose the object you are interested in, you find the F net acting on that object, right? So for example, you have multiple forces acting on it, right? Blah, blah, blah. And then at the end, what you have? MA, right? That's it. That's the Newton's second law. And this is the only equation we used for chapter 5, right? And then center of feather acceleration for circular motion, we have almost the same thing. The only difference is that after you find all forces, F1, F2, F3, and again, still there is a MA, but the only addition here is equals M, A equals B squared over R, which is the center of feather acceleration. So this is just replaced by A for Newton's second law for circular motion. That's the only thing. And then the direction of the force is toward the center of the circle. This makes sense because the acceleration direction is to the center of the circle. So the force direction must be same as the acceleration direction. So this is a full diagram. Again, we start with the constant speed velocity, but we have a center of feather acceleration whose direction is toward the center of the circle because of changes in velocity direction. And then at the same time, we have the same net force acting toward the center of the circle. Right? Because A and F must have the same direction. So a ball, again, the same, example, right? We have here, table, and then you have a pivot, and then you have a string, and then we have a ball, and the ball have a circular motion, right? And again, in order to have a circular motion, the requirement is a net force toward the center of the circle. As you see here, you always need a net force toward the center of the circle, right? So then now, okay, what do you need? You need a net force toward the center of the circle, and then you have to investigate or identify all forces acting on this ball. Of course, there is two forces, normal force and weight, but we're not interested in the vertical motion, but we are interested in the horizontal motion. So the only force acting on this ball is to the tension toward the center of the circle. This makes sense. In other words, F net toward the center of the circle is a tension only. And then again, this is a MA. Again, this is a MV squared over R. This is the basic example of a center of feather acceleration motion. So what force is producing the center of feather acceleration? Of course, in this case, tension. And the same thing, what is the direction of the net force? Again, toward the center of the circle. So answer is P. And the same thing, ice hockey puck is tied by a string. It's exactly the same as what we see previously, right? And then it has a circular motion, and then the force is producing the center of feather acceleration. So what force? Again, the only force acting on this puck in this plane is a tension. So the answer is a tension in the string. Now, the coin is rotating on a turntable. So it moves without sliding at an instant shown in the figure, which arrows gives the direction of the coin's velocity. So the coin is rotating without sliding, right? So that means the coin has a circular motion along this circumference, right? So then what is the direction of the velocity at this point? Direction of the velocity for circular motion or any motion is also what? The tangent of the line, right? So the tangent of this circle at this point is this, right? So the answer is A. What is the direction of the frictional force? Then now again we have to think about the circular motion, right? And then requirement for the circular motion is what? Always you need the net force toward the center of the circle. In other words, in order to maintain a circular motion, you always need net force toward the center of the circle. So then the only force acting on this coin is your friction force to the left, which is the center of the circle. So the answer is B. And the same thing, if the friction force disappear, then what happened? Again, in order to have a circular motion, you need a net force toward the center of the circle. But that force is disappear. So that means you cannot maintain circular motion anymore. So then the coin will simply move along its velocity direction, which is A, right? So then now, so far here, the friction is the only force. Here, the tension is the only force, but it doesn't need to be. You have the object, must have only one force. The requirement is F net gotta be toward the center of the circle. So that doesn't mean F net must have just one force. Sometimes F net force, as we might know, is a combination of more than two forces. So for example, you have a car moving along this partial circumference, making a basically circular motion. So then this is the center of the circle. So in order to maintain this circular motion, the requirement is what? Net force toward the center of the circle. But now let's analyze the forces acting on the car. So the car actually has two forces. Normal force acting upward and the weight acting downwards. But now, in order to, again, have the circular motion, your net force must be always up toward the center of the circle. So that means which force must be greater? Yes, normal force must be greater than this weight. So then your net force is the differences between these two forces. Okay? So this is a force diagram, right? Your normal force vector is gotta be longer than the weight vector so that your net force is over. Okay, so another example, a car is turning a corner at a constant speed. Again, you have a circular motion. And then again, in order to maintain circular motion, which is center of the circle here, so this is the radius r, right? What is necessary? Again, you need the net force toward the center of the circle. So you always need a static friction force toward the center of the circle, right? Again, assuming, this friction force disappear, then what will happen? The car simply move away, cannot make a circular motion. Okay. And then similar question, you have a tube, and then a ball is shoot, through the tube. As the ball emerges from the one end, which path? Of course, everybody know, right? The answer is C, right? So this is why, because there's no, concentrate in this tube anymore to maintain circular motion. So it just, has its previous velocity. And then this is a summary, right? Circular motion involves an acceleration. So it has a net force toward the center of the circle both, right? So we can therefore use technique very similar those we have used, in chapter 5. So the very first, step is, you have to identify all forces acting on the object, and then, draw the force diagram, and then find the net force acting on the object. And then if the net force acting on the object is toward the center of the circle, then now you can say, okay, we'll have a centripetal acceleration and centripetal force. So we have a circular motion, right? So in other words, if the motion is a horizontal plane, right, draw the free body diagram first. And then if motion is a vertical plane, like parallel hills, draw the free body diagram in a vertical view, right? So it doesn't matter, right? And again, everything is what? F net equal. So you have one more steps here, M A. And then A is a V squared over R. So you can say this is a MV squared over R. If sometimes net force is 0, then you can say that's a 0 as well, right? And then use the net force, to determine the speed v, and use the circular kinematics with the, frequency or other details in the motions, right? And then we'll give you the example. So what is the maximum speed with which, 1500 kilogram car can make a turn around the curve with a radius of 20 meter on a level unbanked road without sliding? So then now let's talk about, the situation with the picture. Okay. So then now you can draw the first diagram of this car. Again, you have a normal force up, weight acting downwards, and then static friction force acting to the right. So basically you can set two equations. The first one is a F net force vertical, which is actually N minus W equals 0. So then now you see N is going to be W is a mg. So then now you know mass of the car is a 1500. So g, assuming 10, is a 15000 Newton. So now you have a normal force from the vertical motion. And then now horizontal motion is what? F net x. And then fortunately, friction force is the only force acting on, on the plane, right? But friction force is what? Mu s times a normal force, which is a 15000. And then that equals what? Basically ma, but because this is a circular motion, now you can say this is a v squared over r. So your final answer is simply solving this, where m is a 1500, your r is I think 20 meters, and then mu s is simply 1, so you can cancel. So then now you see your answer is gonna be the v squared is root mu 0 gr. So then now you see this is gonna be 14 meter per second. Okay. So this is not hard, right? So make sure you understand this VJ, examples, and the next one is gonna be a little bit harder. So the next one is again similar situation, but this time this car has a turn on a banked road. Okay, so the curve on a racetrack with a radius of 70 meters is banked at 15 degrees. And then what speed can a car take its curve without assistance from the friction? So this case, we assume there's no friction, right? So this is the differences between previous question, because of the previous question, friction force supply the horizontal force to, or the central force toward the center of the circle. But now, what if we don't have this static friction force? How can we have a horizontal force or net force toward the center of the circle? That's the main idea of this picture, right? This problem. So then now, again, we can draw the force diagram. So first diagram is a pretty similar because we have a normal, the weight acting downwards like a previous question. But now our normal force is slightly tilt because what? Normal force is always perpendicular to the surface, right? But again, like different from the previous question, we don't have a static friction forces. So this is a kind of even simpler problem because we only have two forces actually. But however, this normal force actually consists of two parts, right? So one part is the normal force is a horizontal component, and then the other one is a normal force is a vertical component. So then now you see this case, this three force combination is exactly same as the combination of these three forces. So what the only difference is now this N is replaced by normal force is a vertical component, and this static friction force is replaced by normal force is a horizontal component. So then, okay, now everything is exactly the same as a previous question you see. Because this is a theta. Now you see this is a 90 minus theta. So this is a theta again. So then if you decompose this one and x gotta be, because this is a sine, so this is a, this length is a sine, the n opposite. So this is a sine theta. And this is a, sorry, this y component is gotta be n cosine theta, right? Because this is a adjacent, this is a opposite. So then now again you can set two equations. The first equation is a f net y, the vertical part, which is a n cosine theta is a acting upward, and then w is downward, and again this is 0. So you see n's gotta be w over cosine theta, right? And then now again you can set the second equation f net x, again n sine theta is the only force, but n is what? W cosine theta. So that I will replace this value here directly. So then that is a W sine theta over cosine theta, which is a tangent theta. So I'll say W is mg, and I say this is a tangent theta. And then this force is what? M b squared over r for the circular motion. Then now you see cancel m. So now you're looking for the velocity. So v is gonna be rg tan theta. So v squared is rg tan theta. So now you have a v is a rg tan theta, right? So your, this is your horizontal force, and this is your vertical force as we did before. And then you see your velocity will be rg tangent theta. Again, you see the velocity will be 14 meter per second. Okay, so this is it. So the what we did today is kind of a new things because we have a new concept about frequency and then period, and then you see RPM. But again, if you know one of them, you know the other three at the same time, right? And then what is the requirement to have the circular motion? Requirement for the circular motion is always you need net force toward the center of the circle. So make sure you understand, fully understand last two example I presented here today. Okay, so I believe if you understand these two questions, you must be fine. Okay, and then if you have any question, let me know. You can send me an email. We can have a Zoom meeting whenever you need it. Thank you.